In this video, I will give you an introduction to the Bernoulli effect. And I have mentioned in the past that when we have an incompressible fluid and the diameter of our fluid is decreased, the speed increases. So here, this will be the velocity of the fluid, whereas here the fluid is moving a little bit slower. Now, this is with these two velocity vectors, I am describing the motion. I know from the equation of continuity, and I know from experiments, perhaps, that when the diameter decreases, when the area decreases, the speed, the velocity of the fluid increases. So I have a description of the motion. Now let's see if we say that this is the initial and this is the final. Now I'm gonna draw those two vectors here. This is the initial, this is the final. This means that the change in the velocity vector will be pointing to the right. Now, because I know that momentum in classical mechanics is approximately the mass times velocity, this means that the initial momentum will point to the right, and the final momentum, the final will also point to the right, and the arrow will be longer, and also the change in momentum will point to the right as well. Now, how do I know that this is the change in momentum? If you start with the initial, you start from here, you go here, and you think, what do I need to add to the initial momentum to get to the final? Well, if the initial brings you from here to here, then you need to add this in order to make it all the way to the final. That's why this is the change in the momentum. Now, if the change in momentum points to the right, then I know from Newton's second law this is Newton's second law. The change in the momentum of the system over the change in time is equal to the net force. Now, if the change in momentum points to the right, this means that I need to have a net force acting on the system that is also pointing to the right, since delta t is always a positive number. So I know from the description of the motion of the fluid, I know that the velocity increases as the fluid flows from here to here. This means that the momentum also increases, and the change in the momentum points to the right, which means there has to be a net force that is causing, it is important to note, this is the cause of the speed up of the fluid from here to here. There has to be a net force. Now, the way that I will do this, the way that I will find out what that gives me, I will say I'm gonna choose a portion of the fluid, let's say this, and I'm gonna make this to be my system. So this over here, this is my system. And I have chosen it specifically to be right in between this left portion of the fluid that is moving slower and the one that is to the right that is moving faster. The net force on the system needs to be to the right. Now I need to think about, well, how many forces are acting on this? Let's say if I draw my system here again. This is my system. And now I'm gonna draw the fluid that surrounds the two Let's use slightly different color. Let's make this so let's do one and then another one. Let's do this again. All right. Now these are the parts of the fluid that surround my system. Of course, the fluid is three-dimensional, so you can think that there is one that is out of the board and another one that is behind the system that we cannot see. But for now, I'm just showing the ones that are on this plane. Let's call this left. Let's call this right, top, bottom. And there is, of course, as I said, one, since a cube has 6 sides, I'm only drawing the fluid that is adjacent to 4 of the sides of the cube. There are 2 more, as I said. I'm not gonna worry about those because those will be similar to the top and bottom. I know that the fluid is only speeding up to the right. This means that the force, there is a force from the contact force from the top to my system. There is a contact force from the bottom on the system, this part of the fluid. And there is a contact force from the left fluid on the system, plus there is a contact force from the right on the system. Now, because I know that the net force points to the right, this means the force that the top fluid exerts on the system should be cancelled out by the contact force the bottom part of the fluid exerts on the system. So this is pushing on my system downwards, this is pushing on my system upwards. The 2 will cancel out, so this will be cancelled out from that. And the same thing happens, as I said, from the other 2 sides of the cube. However, because the contact force, this is the contact force that the left part of the fluid exerts on the system, and this is the contact force that the right part of the fluid exerts on my system. I know that the net force points to the right. I found that previously. Since there is only one force pointing to the right and one force pointing to the left, and the net force is to the right, this means that this is a greater force. So drawing the forces here on my system that is part of the fluid, there is a large force from here, from this portion of the fluid on the system, and there is a smaller force that is pushing my system, a smaller force from here on my system that is pushing it backwards. As I said though, the net force is to the right, which is true if you get this short arrow, and if you add it to the long arrow to the right, you do get a net force on my system that's pointing to the right, which is why the fluid is speeding up. Now, we know, we have seen in the past that we define the pressure to be the force divided by the area. Which means if you increase the force you also increase the pressure. And because this, let's say this is the left portion of the fluid, because the left portion of the fluid exerts a large force on my system, and force is proportional to pressure, this means that here I will have a large pressure. Now, because this right portion, what is on the right of my system, is associated with this small force, this is why this portion of the fluid is also associated with a small pressure. So here we have a large pressure. Here we have a small. Here we have a small pressure. This is the Bernoulli effect. When the fluid is moving slowly, see here I have a small velocity, I have a large pressure. In the areas where the fluid is moving fast, I have a small pressure. This is what we call the Bernoulli effect. So when you hear about the Bernoulli effect, it means you have a small speed, large pressure, and then when the speed is large, you end up having a small pressure. And using Newton's second law, I explained how you can prove that the pressure here is large and the pressure here is small. And this over here is what we call the Bernoulli effect. Now there is an important application of the Bernoulli effect. Let's say we have a house. And here is the roof. Oops, nope. Here is the roof. There are times where, of course, there is air both inside and outside. And let's say there is some wind flowing. Okay, as the wind is flowing, it's going here, and of course it goes around the roof, and then it's going away. Now, and I want to remind you that air is a fluid. So in my previous example where I used Newton's second law, I was thinking about a liquid flowing, but liquids are not the only fluids. Air that surrounds us is also a fluid. Now, of course, you have air both inside the house and outside the house. The air, though, inside the house is moving at with a small speed, if at all. This means that there is a large pressure on the walls of the house, and of course that includes the roof. Okay, the same thing if you, let's do here. Okay, small speed, large pressure everywhere. Now, assuming that the weather conditions are such that you also have a small speed outside the house, the pressure out from outside to inside will also be large. And you will have two pressures, one from outside, one from inside, on the roof. They essentially balance each other out and they cancel out and everything is fine. There are, though, cases where the wind, the air, is moving outside of the house with a large speed. And one of those weather conditions are the tornadoes, where the speed of the air is very large, much larger than what you have typically in the interior of the house. This means that there will be, outside the house, there will be a very small pressure. A very small pressure would be, let's say, a tiny arrow that's pushing on your roof, like this. And now the problem is that the two pressures, all the forces acting from the inside air, and they're pushing on the roof outwards, they cannot be counterbalanced. They cannot be cancelled out with the tiny forces that the air outside exerts on the roof. And when that happens, there is a large force from the air inside the house to the roof. That force is not cancelled out by any forces from the outside air, and this is why you end up seeing the roofs flying away. This is an unfortunate result of the Bernoulli effect, where the pressure from inside air to the roof of the house can have as a result the roof of the house to move away. This is an application of the Bernoulli effect.